to get the last talk, which is hardware updates, which I was assigned. Further, I think that is like take home message, so summary. What we have shown. So I'm lucky that Christopher knows that redundancy is a useful thing. So let's do it 11, and I will just review all the slides that you already have seen during the talks, because there's nothing to do. Okay, I'm joking. I have something new to show you around also. But when I was watching, I was like, okay, that's crossover. Like you already seen that. So, but yes, we launched a few new stuff. We mostly try to show you also the lab those things. So the universal goniometer 3 or UG3 as we call it. Correctly, I hope that. We still don't have it in lab, but it's coming. I would tell you a few things about it. There is IGH2, IGH3 update from our intelligent goniometer head. IGH3 is the one that goes with the new goniometer that you already heard about it. I tried to show you on the lab tool the intelligent optic models, which we have now available for the most versatile rotating anode system. And we recently launched also the new microfocus CirQ system for anyone that is still not convinced to Rigaku rotating anode solutions and still want to stay with simple source solution. So this slide probably you have seen already. So just as a repetition, we discussed the goniometer need to keep up with our sources. So we upgraded and built better sources, and then we figured out that the goniometer need to have a refresh also. But we also put more effort on this software control. So everything goes to the software, because nowadays you need that to be the software. I know that lots of people are still hoping for buttons, physical buttons, but at the end, everyday works is that you can log on to TeamViewer and do everything from TeamViewer from your office or from that house in Scotland, and not have to show up in the lab to press one button. So we
press the button, would you?
Yes. So there is lots of updates, that you don't see on the first place, but the goniometer is getting modernized, updated, and more faster. And we also changed something for lighting for visualization, which I can show you because I got a few new slides. And the whole thing is moving to more as a robot. So I remember when I was still getting first CAD 4 instrument, like my professor was saying, oh, that's a fully automated goniometer. It's like a robot. So I don't remember times when the goniometer were not automated, but I had stories that there were not automated goniometers. But we all now forget about it, that it's actually a very clever robot that we using inside of your diffractometer. So it got updated with the latest robotic position sensor, the same one that you have seen the robot arm using in our cabinet. It's very similar now also for your robot that actually drives your sample around during the measurements. So this slide probably also, so this is what I mentioned earlier. So cryo device, we improved to be more reliable, faster motor speeds, integrated goniometer head, and this I think Matthias also show you the benefits. So we need to 20 faster scanning speeds. So the whole thing is smaller, lighter, so we can move faster. But that means that we also have a look, and we built extra detector, super detector that is dedicated for single crystal measurements. We discussed that in the lab. We can now finally build the curve detectors again because of the high dynamic range of those modules. So you can register both high angle and low angle at the same time. And the goniometer had to follow next because the arcs have straight shape that the former goniometer didn't really expected. So the biggest change that you can see, if I have a pointer, probably not. Yeah, I can switch to the pointer, but the biggest change is probably you can see on the picture is here, and that goes because of the presence of the arcs of our goniometer. And this is the movie from Chris making from the mock-up that we had on the Padova. What I want to show, he was playing with the new beam stop, but what I want to show you is the thing that hopefully will come back is on loop. In this corner, is this strange box that you probably briefly can spot it. So this is our new sample lighting system. And if you had a training with me, or you are protein crystallographers, you end up very often with the plastic ruler with the piece white of paper on the back. Because if you don't mount crystal correctly and you put too much oil with it, then you will see something like that and you will wonder where is your crystal. So when I go for training, it's an easy trick. You put a piece of paper under your loop. But you cannot do that when you use a team viewer, because you are not in front of your system. So the guys in R&D figure out this way to trick with extra lighting, a way to make those effects that usually are coming from a way how you mount the sample disappear. So you can see how much we improved the images of the crystal inside the drops, also inside the capillaries. All the capillaries with moving reflections, and that's always connected to what we want to do. We want to center automatically for you, so or with the half hour 2 clicks. For that, you need a better image on your loops. So that's another effect of it. So iteration goniometer head, you've probably seen this slide already, so I'll just leave it for the second. For I think what is not mentioned when I show one of the groups, we have a pin sensor on now built into to do both goniometer heads, so we know exactly if the pin is mounted or not. That's more important for the non-attended robot works, but also just prevents you to not have to look inside the cabinet if I left the pin on, or whether should the cover, because the system always know if it's there. So I recorded some movies from earlier tests to show you how the X-ray centric works. I didn't have time to show it because I told you, as Matthias also mentioned, it takes time. So I showed her the card. This is like a dirty loop with properly mounted crystals. So you see it's a nice visible. So I will center that optically. So that's just a test of the system to show you performance. But if you are not there and your robot is mounting your sample, you have to be sure how it's centric. So you see how it works. So it generates the mesh that was on the loop side. Then he create a space around this mesh, create those paths that intersect in 3D space. So the sample have two colors, see moving in 3D space, and then he just basically scan the whole thing and find the best spot when you have the best diffraction. And for this is done on a seal tube system, on the flow seal tube system, and it should take less than 15 minutes for most of the samples that I tested. I will show you also time predictions in the second. So, yeah, so now let's go back again. So it's on a loop, so you have seen the whole process already. So of course that's 16 times faster to make it more reliable. So I have more challenging samples. I use rotating anode for this one. The copper one, you can see that the voltage is over there. So you can see the crystal because I put it on purpose, so you can see, so I can verify that the centric, so you can see that it works. Because this is the example when the crystal is so small that you basically cannot see it. Or you mounted it flat and you will see it. So this is on purpose that you can see that small bit of things sticking out. Again, a properly mounted sample, so on top without the oil. So there is no need in hiding, but you can see how quickly the software identify the crystal, find those paths, and just proceed. And then this movie, if you are patient, I actually collect data set to show you this extremely flat scale plot that you're getting when you do that with the small crystal. If you do that only just by placing a tip of it, you will get instantly like this. So I speed up 8 times, not six times, so we have to wait. Hopefully I will not run out of time, but it's almost there. So it takes on a small system on rotating anode around 10 minutes. If you stop, there was a time. So you see now I just go straight forward to the data collections, use the workflow in a Crystallis Pro, and at the end you will see the flat scale plot that is coming from this centric. So it's not only verified optically, but also with X-rays and experiment that the X-ray centric is doing good work. So that's the full recording. So I get you a proof of that this work like on the movie. So a few seconds of recording. Of course, it's a copper rotating anode, so we even with 8x6 it's already too fast to even spot that it's moving. So it was still UG2, so it was so slow. I'm sorry about that. UG3 would be faster, of course. So you see from it didn't stop from the but you have seen briefly this slide. I hope that for that setup. But anyway, the other thing that we added for the other way is that I was on the training with one of the first users, and we said about it like but can I just select an area where I know where I put the crystals, because I'm sloppy and I put the crystal dot where you expect to have a crystal dot at upper loop, but it's somewhere here, and I know it is there, but I cannot see it. So you have this manual selected of region of interest, and then you just point like the crystal should be somewhere there, and then similarly, like you see the crystal scroll will take over and continue to do this. So for this one, it's really needed. We needed really update on the goniometer head, because you moving the crystals in the 3D space, so you losing this ability to check with the camera your feedback for your movement, because you're moving crystals also out of the plane of the camera. So you have to be really trusting your goniometer head. So that's why the IGH2, IGH3 with the better encoders, robot style encoders, which we trust that if you go there and start scanning from this path of the space, it goes straight to exactly like we do. So that's why it's enabled only on the latest generators of the goniometer head. So it was a fun process to work with the software team. I think you have similar picture in your coffee place in Wrocław, and I sometimes very glad. So that's my process of testing new features in with software team, and then usually this what happens, and then I switch to OLX2 when I'm waiting for reply. So we started with such a thing, and I instantly maxed out everything, and I complained that it works. So I added a timer, and I realized, okay, maybe I'm using it wrong, because they calculated, yes, if you use these settings like this, you're expecting about 2 hours of grid searching your crystals around the space that you define as to work. So after some discussions and machine learnings, we simplify for you something that you have a well diffracting, which on our DW is taken from here, is predicted to be around 7 minutes, and weak diffracting, which should be 8 minutes. As I told you, my practical test is that 10 plus, if you got lucky, you are getting these numbers. If you have to do some more scans, you end up with 10, 15 minutes, which is still extremely quick for home lab based system. And for the robot operation, you don't notice this if you want to have a better instance. So the next thing that you are showing, there was a picture how it looks inside. To be honest, I don't know. I think Fraser did this rendering, so I don't know how much it's outer imagination, how much is smooth. But
it's a representation.
It's a representation. So we will not tell you how it looks inside. So this is when you were showing, I was showing how it's done. This is how it's that we show it to it move. And you can see those beams that I show you on the burning paper, how it can move. This is how it's done. And you can see our rotating anode, dual waving rotating anode. And then you can see on the second part of the image, another sub-occupation which I showed you when you're switching the wavelengths, which some of you also want to see, and I'll show you. It really just takes 5 minutes to get the moly and copper back. So if you don't care for your scale factors, you can just continue measurements instantly just after. So that's highly, like every generation, every upgrade is getting better, as you can see, and less screws, less knobs. So this one has nothing that the user can touch. Everything is software control of this version. So that gives us to the GUI that I was showing around. So I just want to show you the benchmark performance that I did for you, how it's done. So the procedure looks like this. So you center the pinhole tool automatically. So you have seen it. I just put the tool, run the procedure, and the robot will take care of everything for you. So he would center the pinhole tool, then offset to the lateral position. So we move away the pinhole from the beam. Then we'll go optimize the flux of the beam. So he will maximize performance of your source. And then he will recenter, move, walk the beam, the tool, and then he walk the beam through the hole. So putting in the center of goniometer. And how much time it takes? So this is the movie that also Matthias already show. I have to skip the movies because I see Fraser looking on the watch. So you have seen it already. So the surprising, the IGH1 we kind of supported again to back compatibility. So it works. I checked. It's not officially support, but I worked checked. It's slightly quicker than IGH2, IGH3, but I would say less reliable. But you can still want to use it because when I tested, it's still more repetitively doing if I'm doing myself manual, even on IGH1. If human cannot repeat exactly the same task over and over again, robots are very good with this. So I tested even on the older goniometer head. It's even faster. It's just a few minutes to center the optically center the hole on the system, and then the beam optimization. There's too fast and full. We talk about it during that, so it's less than 30 minutes or 90 minutes, and the full program, depending on how you set up this, is 30 minutes to completely starting from scratch to 2.5 hours, so it's not bad. So I took, before using a meeting, I ran it with several scenario, and I just copy from the logs. So you have to combine those two numbers. So this is with energy discrimination, and this is leaving the energy discrimination at the back. You can see I apply my tested profile GUI testing procedure, and we move some settings that are necessary to the settings button. So at least you don't have to now work for it. So energy discrimination. So it's fancy, but it's basically that our sources are always aligned on the more intense alpha peak. Unless if you are interested in this peak, which this is the result of scanning of the aligning system, you can find it in the log files. If you are interested in this peak, you go to Regensburg, and they will explain you why you might want to disable this option in this extra options. So the robot will not always place you on the proper wavelengths, but that's another completely topic for you. So the last thing is that on my agenda. I hope I was not super fast and.
You still have more than 5 minutes.
Okay. Yeah.
You can slow down if you want.
Okay. So it's our new source. Again, the slides somewhere show up. So we also updated the goniometer for our seal tube system. So we have a faster goniometer, so we can put the faster source matching our new goniometers. And we completely want to maximize performance without really compromising your cost operation, because this is our instrument that we know that people that just want to have a nice working instrument at home, not too fast, not too expensive to run. So I want to show you what this asterisk means, because I got lucky to do actually the test. So Fraser did a nice slide about showing the difference in the source. So it looks not much change design, but there is lots of redesign how we condition the beam. So you can see mostly that the beam is slightly smaller on the sample position, and we basically grabbing more photons from the target itself and guiding it through the optic chamber to your sample position. So what it can do for you? So this is the slide also you have seen. So basically we check using standard crystal, but not only that we getting more photons on the detector, and that what actually always what matter. That of course means the more background, more other things. So the signal to noise is proportionally, and then it trickle down. So I want to show you that what crystals I use. So for me, those are the standard crystal size that I use on our system, and I was told that they are quite small, but this is what I usually measure. I give you usually the times that I'm using of it. So the last one is the typical one that you almost don't see, but this is our rack size crystal. What I would say use it. You can still measure it on the seal tube system, but it's just taking longer. So, but I also use other crystals, also badly mounted for specific reason, but also we tested with different compounds. I don't have time to show all the results at this, but I just want to show you that we tested. And we did it a proper test, so we used the same actually tube. So the team in Wrocław was incredible. I have never seen the whole goniometer rebuilt basically in the time when I go for the coffee and was coming back, and the whole new source was on the system back waiting, so we didn't have to move everything. So it looks slightly strange because of the cables and everything, but basically I was able to even keep the crystal on the goniometer and get the new source done. So we make very careful that even if I remounted the crystal, I was carefully made sure that it's mounted exactly the same way. There are some ways to do it, and Crystallize Pro allows you to check what was the orientation matrix, so you can see how good roughly I did. So I did all the best, also processing data set to make sure that we comparing apples to apples, all the stuff was selected, and basically the results are in. And I calculated some numbers. Those were from that titled in, so you can see the relative volume. And I was quite interested in those I to sigma percentage. So I ran also several strategic, different distance, different kind of strategies to get the average this number right. So I spread you something, because if you're using Crystallize Pro and you're all using Crystallize Pro, you know that if I get this empirical value ready, I can just use simulator and tell you everything what you want to know, what's the difference between the sources. You don't have to really measure it. But it's not only about the speed, it's also about the quality. Here you can see, of course, I was using here Nosferatu, but you can see the data sets are on the same amount of the reflections. I used a special tool in Crystallize Pro that does the same HKLs, and you can see the same crystal with the same orientation, how it improves your data quality. So if there was discussion, should we collect better data? Yes, you can collect better data. Also, a badly mounted crystal done on purpose to correct basically, can I say, like borderline data set in a shortest time, to show that we not only collect quicker and more intense data, but we also see more observability. So the source is brighter. Also, we see the same on the protein sample, but for you, it's mostly things. So you can see that with more photons on the sample, it's still factor free, but that translates to I'm showing on the wrong screen, so yeah, try to show you something, but okay. So you can see that observability of the reflection grows. It's crucial if you want to do what it is from very small or bad crystals, because that 1 angstrom is apparently for cancellation. Horst mentioned recently that there is a software coming that allows you to solve the structure from 2 angstrom dataset, so maybe the whole work was not necessary. But unless we get the software in OLEX, we still need that 1 angstrom data from your crystals to solve it. So that's a big improvement. And you can see that also that shows in the refinement. So you can see that's X-ray data, but on purpose collected almost like ED data. So extremely low I to sigma. Our detectors allows you to collect such a data because we don't have noise on the detectors. So you can trust this data to solve and refine. And they are both below 10%. So maybe not the best structure, but if you look on database in CD, you find lots of such structures somewhere sneaking in. So not bad. So as I said, so I did all this test to get some input for our simulator, so I can show you how it is. So on basic side, it doesn't look a lot. It's like 20 minutes, 45 minutes. What the heck would is it? But if I go for slightly better data collection, I don't know if you can see it. I just put the redundancy 5 and I collecting for the point group. So basically a proper data quality calculation. So I'm jumping from 2 hours to 5 hours. So it is really an upgrade for your microfocus system, because it reduces in half, but it only notices when the data sets are getting longer. Yeah. So if you're talking 10 minutes, 5 minutes, but you will get the samples that you want to collect for absolute structure, and then it will be 2 hours. So that's the thing that you can see. And we also did this this is my invention, so it's not really accurate, but I make some Excel sheet correlation, and I really can show that on the smaller crystals are getting better results. So the beam is brighter, not only more photons coming through the crystal itself. And you can see I could clearly notice that I reduced the amount of exposure time to get the same quality data on the tubes to this one. And yes, you could collect data at the same time. So I had this slide done already, so it's not like I say that collect bad data. If you have a better source, you can collect better data at the same time. So rather than doing 45, so you can see in 45 on the PhotonJet-S, I can collect like 5 redundancy, and then I can collect redundancy 12 and much better data set with higher I to sigma, either a higher I to sigma or redundancy, you choose what you prefer on your data set, but you can use this extra performance of YouTube to just collect better data in the same time. And yes, and I don't list them, but I hope that you see that the automation is coming. We have to be ready, and our company and products are ready for the automation, for the new way to develop, but we also not forgetting about the small stuff like better lighting, better source, also not only rotating a lot, but also still chip system. So that's the end for me. Did I make it in time?